Atoms is one of the most scoring topic, and you can expect question in chemistry as well as in physics. So what I have done in this one short video, so I have divided this video into two parts. In the first part, we'll see what is the syllabus, and then we'll systematically go through the mind map and see different areas that we have to study. And in the second part, I have divided the numericals into 5 problem types, and we'll see, I'll take up questions from last 3 years of JEE, so that you have the idea how to apply the concept. So without any further delay, let's start. So this year's syllabus is exactly same as the last year's syllabus. And let us see the syllabus. So first we have alpha particle scattering experiment, and then Rutherford's model of atom, and then Bohr's model, energy level, and hydrogen spectrum. Okay, now let us go into the depth of this syllabus with the help of a mind map. So first we'll see the old models like the Plum pudding model, then Thompson model, and then we'll see the Bohr model. And in Bohr's model, we'll see the postulates, and then the different physical quantities that are associated with the electron, for example, the orbital radius, and then the speed of the electron, angular speed, and frequency, time period. All these physical quantities will derive in this video. And also we'll also see what is the energy of the system of the atom, right? Kinetic energy of the electron, potential energy, and the total energy. And then we'll see what is excitation of the electron, what is ionization energy of the atom, and then the de-excitation, where we'll study the different spectral lines. And if suppose if we have a hypothetical model which is not like a hydrogen atom, or we have say some other particle instead of an electron, suppose some hypothetical particle, then how to apply Bohr's model in that model, in that particular question. Okay, now let us see the two old models which we have discontinued because they are not able to explain some basic phenomena. So first is the Plum pudding model. So this model was given by Thompson. According to this model, the atom basically is what? So the positive charge is uniformly distributed in a sphere, and the electrons are embedded in that sphere like this. So electrons are not moving, they are static. So just remember this thing. And then let us come to the Rutherford's atomic model. So it is very important. So first of all, you must have studied about Rutherford scattering in your class 9th, right? So I'm not going into that detail, but let us see some important observation. So first of all, most of the alpha particles passes through the foil undeflected, right? So what does it mean? So there are lots of empty spaces inside the atom. So most of the alpha particles suffer no deflection, and there are several alpha particles deflected from their original direction by large angles, right? And very few are observed to be reflected back, reversing their direction of travel. So what does it mean? So if they are completely rebounding, so if you take a case of a ball, if you're throwing a ball on the wall, what happens? The ball just rebounds back. Same is the case, and there will be some alpha particle which rebounds back. It means there must be something dense present in the atom, and that dense entity is nothing but the nucleus. So we can see the majority of the positive charge of the nucleus is concentrated in the nucleus, and due to that dense positively charged entity present in the atom, the alpha particle experience strong electrostatic repulsion, and it completely retraces its path. So what do you have to remember? So you have to remember this graph. So on the y-axis, we have the number of particles which are getting scattered, number of alpha particle, number of scattered particle, and on the x-axis, we have angle of scattering. Now, what is angle of scattering? Suppose if this is the alpha particle, it is coming in this direction, and here we have the nucleus. And suppose this alpha particle deviated like this, right? So this is the velocity after scattering. So what is the deflection produced in the alpha particle? So we can find the deflection produced. So this angle is known as the angle of scattering. So this is angle of scattering. So if we plot this graph, so experimentally this graph comes out to be proportional. So this n will comes out to be proportional to fourth power of cosecant theta by 2. So do remember this proportionality. There can be a question based on this proportionality. Right. So now, what are the inferences of this particular experiment? So first, the positive charge in the atom was concentrated in the region that was which was very small in comparison to the size of the atom. Right. And this positive charge is known as the nucleus, and electrons are moving in a large volume of the atom outside the nucleus. So these are the inferences of the Rutherford model. Now there are some like phenomena which Rutherford was not able to explain, and first is it can't explain the line spectrum of the hydrogen atom, and according to Rutherford, it should be having a continuous spectrum, because when a charged particle is accelerating, it is keeps on radiating energy in the form of electromagnetic radiation. So if that is happening, we should get a range, we should get an entire spectrum, rather some discrete wavelengths. So it was not able to explain. If you want to go through the justification, just read this, you will get the idea. So I'm not going into that detail. So it could not able to explain the stability of the atom. So again, if the electron is radiating energy, it will lose energy and ultimately it will bombard on the nucleus, but we know atoms are stable. So these two important phenomena Rutherford was not able to explain. So then we come to the okay, right. So as I mentioned in the beginning, I have divided this one shot into 5 problem types. So now let us see the first type of the problem, which is based on the distance of closest approach. Okay, right. So what is this type of problem? Let us see. Suppose we have given an alpha particle, and this alpha particle has some initial energy Ki. Okay, and it is moving towards a nucleus. Towards the nucleus, and this nucleus has an atomic number Z, and it's, you can say the charge on this nucleus will be Ze, right? Now the impact parameter, or you can say the line of motion of the alpha particle passes through the center of the nucleus, and due to strong electrostatic repulsion, the alpha particle, let us assume that the alpha particle comes to for a momentary rest at this particular point. So here the velocity will become 0. Now this distance is known as the distance of closest approach. And we are assuming that when the energy of the alpha particle was Ki, it was quite far from the nucleus. So they are not interacting at that point of time. So what is happening here? So there is a loss of kinetic energy and gain in the electrostatic potential energy. So if we want to find this R minimum, we can apply energy conservation. So if I apply energy conservation, so K initial, so this is the loss in kinetic energy, and gain in the electrostatic potential energy will be K Q1 Q2 by R, right? So K and Q here is charge of the alpha particle, and Z is the charge of the nucleus divided by R minimum. So from here R minimum comes out to be KQ ZE upon KI. Okay, so this formula you will get. So do remember this formula. Now let us see the application of that. An alpha particle with kinetic energy of 10 mega electron volt is heading towards a stationary point nucleus of atomic number 50. So what is the distance of closest approach? So we know that R minimum in this particular case will be K times Q times ZE divided by K initial. So K is 9 into 10 raised to power 9, and the charge on the alpha particle is 2 times the charge on the electron. So 2 times 1.6 into 10 raised to power minus 19, and the atomic number is given as 50. Again we have, so it will become E square, right? Divided by kinetic energy, which is 10 mega. So mega is 10 raised to power 6, and 1 electron volt is 1.6 into 10 raised to power minus 19 joules. 1.6 into 10 raised to power minus 19. So 1 E will get cancelled out. So we will have 9 times 2 times 1.6 times 50 into 10 raised to power minus 10 and minus 7. So let us simplify this. So this 2 and 50 will become 100. So we have 9 into 160 into 10 raised to power minus 17. And this comes out to be 144 into 10 raised to power minus 16, or we can say it will be 14.4 into 10 raised to power minus 15 meters. And we know that 10 raised to power minus 15 meter is nothing but Fermi, right? So we can write this as 14.4 Fermi. So that is the distance of closest approach in this particular question. Right. So now let us see the second problem type, which is based on the impact parameter. Now, what is the impact parameter? Suppose this is the nucleus and this is the alpha particle, and the line of motion, if you look at the line of motion of the alpha particle, it is at a certain distance from the central line passing through the nucleus. Now the distance between these two parallel lines is known as the impact parameter, and this alpha is nothing but the angle of scattering, right? And that we have already discussed in Rutherford scattering case, right? So do remember this formula, which say where q1 is the charge of the alpha particle. So let us say it has a charge q1 and nucleus is having a charge q2, and the initial kinetic energy of the alpha particle is ki, and theta is the angle of scattering. Okay, so now let us see, so this k q1 q2 upon 2 times ki times cot theta by 2. So let us see the question based on this formula which came in JEE. Now root d1 and root d2 are the impact parameter corresponding to scattering angles 60 degrees and 90 degrees respectively. When an alpha particle is approaching a gold nucleus, for d1 is equals to x times d2, the value of x will be, right? So here they have given impact. So basically we have to find the relation between impact parameter. So we are going to use this formula. So B is k q1 q2 divided by 2 times ki cot theta by 2, right? Where theta is the angle of scattering. So can you see this factor is same for both the cases? So we can say b1 by b2 will be equals to cot theta 1 by 2 upon cot theta 2 by 2. So we can apply this proportionality, and b1 is given as root of d1 and b2 is given as root of d2, and theta 1 is given as 60 degrees, so it becomes 30 degree, and theta 2 is 90, so it becomes 45 degrees. So cot 30 is nothing but root 3, and cot 45 is 1. So now let us square on both sides. So this will become d1 by d2 is equals to 3. So x comes out to be 3. So 3 is the answer. Right. So now let us see the third problem types, and the third problem type will be based on Bohr's postulates, right? So first we'll understand what are the postulates, and then we'll see some derivations which of radius or and then the speed and then the angular velocity, current, and different other physical quantities, and then we'll go to the previous year's questions. Okay, now let us see the postulates of Bohr's model. So first postulate states that if we have a nucleus, positively charged nucleus, then the electron is orbiting with the help of the Coulomb attraction between the electron and the nucleus. So the Coulomb attraction is nothing but the agent which is providing the centripetal force. So Fe will be Fc. So we can say K times Ze times E by R square will be mv square by R. So we can apply this equation. Now the second postulate states that if the electron is orbiting in a particular orbit, then its angular momentum is conserved and it will be given by h upon 2 pi. So nh upon 2 pi. So this is the angular momentum, and we know if a particle is orbiting in a circle, then its angular momentum will be given by, in magnitude, will be given by mvr, right? So this is the angular momentum. So you should remember this equation also, m, v, and rn, where n stands for the nth. So nth with speed of the electron in the nth orbit will be vn, and the radius of the nth orbit will be rn, right? So nh upon 2 pi. And the third thing, when the electron is orbiting in a particular orbit, it does not radiate energy. It only radiate energy if it is coming from a higher energy level to a lower energy level. So suppose this is the nucleus, and let us say this is, say, second orbit, and this is the fourth orbit, right? So if the electron jumps from the fourth orbit to the second orbit, it radiates a photon of energy which is nothing but E4 minus E2, difference of the energies of the two levels. So do remember these three postulates. Now let us derive let us derive the radius of the nth orbit. So we are going to use the postulates, first two postulates. So according to first postulate, Fc is equals to Fe. So we can say m Vn square upon Rn will be equals to K times Ze times E divided by Rn square. So 1 Rn will get cancelled out. So we can write this as m Vn Rn times Vn. So this will be K Ze square. Okay. And we know that m, v, and Rn is nothing but the angular momentum. So if the electron is orbiting in the nth orbit, so this will be nh upon 2 pi. So from this equation, we will get the speed, right? So we can say Vn will be kZe square divided by nh times 2 pi. Okay, so if you look at the proportionality, so we can say Vn is equals to 2 pi k e square upon h times z by n. So Vn is directly proportional to the atomic number of the atom. It is inversely proportional to the principal quantum number, you can say n. And do remember this, Bohr's model is applicable for single electron species. So if I say, for example, let me also mention here, it is applicable for isoelectronic species like hydrogen is there, and then we have helium plus, lithium 2 plus, like this. Okay, so do remember this. And suppose if we are talking about lithium 2 plus, in that case the Z will be 3. For helium it will be 2. Right. So if we look at this vector, it has all known quantities, right? So K is 9 into 10 raised to power 9, E is the charge on the electron, H is the Planck's constant. So if we calculate, if we plug in the value, we will get Vn equals to 2.18 into 10 raised to power 6 Z by n. So you should remember this equation. So there are straightforward questions from this formula. Now we want to find the radius. So how we can find the radius? Let us substitute Vn in the angular momentum formula. So we can say m Rn 2 pi k e square upon h z by n times equals to nh upon 2 pi. So from this, let us simplify this. So Rn will be n square h square upon 4 pi square k e square m z. So can you see in the velocity formula, m is not there. So we can say Vn does not depends upon mass, but radius depends upon mass. It is inversely proportional to the mass of the electron, right? So we can say Rn is equals to h square upon 4 pi square k e square m n square by z. Again, there is a factor which contains known quantities. So if we simplify this, we will get a radius of the nth orbit as 0.529 angstrom times n square by z. So do remember this formula. Okay. So this is the formula that you have to remember. And suppose if we have lithium 2 plus, then Z will be 3. And if you want to find the radius of the third orbit, then small n is also 3. So like this, we can calculate the radius quite easily. So velocity we have already derived in the last section, that is 2.18 into 10 to the power 6 Z by n. So do remember this proportionality. Now the linear momentum is nothing but mass times the velocity. So it becomes this. And you have to remember this proportionality Z by n. Angular velocity is nothing but Vn by Rn, right? And we know that Vn is directly proportional to Z by n and Rn is directly proportional to n square by z. So if we take the ratio of these two, then it becomes Z by n, then we have n square by z. So this will be Z square by n cube. Okay, so you do remember this proportionality. Now the time period of one orbit, right? So it will be one revolution. So time period is 2 pi by omega n, and omega we have just calculated. So time period will be inversely proportional to this, the proportion in terms of proportionality. So it becomes n cube by z square, right? Next is the frequency. Frequency is nothing but omega n upon 2 pi. Again, it will be having same proportionality, z square upon n cube. Orbital current. So if a charge is orbiting in a circle of radius, let us say if radius is r, right? If there is a charge q and it is orbiting and the frequency is f, so the current will be given by the charge times the frequency. So we can say the current is directly proportional to the frequency. So again, the proportionality will be z square upon n cube. Angular momentum, it is the postulate. It is directly proportional to n. And if you talk about centripetal acceleration is Vn square by Rn. And we know that Vn is directly proportional to Z by n and Rn is directly proportional to n square by Z. So we can say AC will be directly proportional to Z square by n square times Z by n square. So this will become Z cube by n raised to power 4. Now let us derive the kinetic energy, potential energy, and the total energy or mechanical energy. Right, so I need the formula for speed. So kinetic energy is half m Vn square. So if we substitute the value of Vn, we will get this formula, right? And if we plug in the values for known quantities, we will get 13.6 times z square by n square in electron volt, right? So 13.6 z square by n square. Do remember this formula. And potential energy will be given by k q1 q2 by Rn, or I can write with a or I can write the, let us put the charge. So Ze, and then it will be negative, right? K Ze square upon Rn. If you substitute the value of Rn, we will get Un, right? And it comes out to be minus 27.2 Z square by n square in electron volt. Now if we add these two, we will get this, right? So which is minus 13.6 Z square by n square. So do remember these three formulas. And if we substitute n equals to 1 in the mechanical energy, we'll get minus 13.6 Z square. If we substitute 2, we'll get minus 3.4. If we substitute 3, we will get minus 1.5 and then minus 0.85, then minus 0.54 and minus 0.36. So this is the energy of first orbit, second, third, fourth, fifth, and sixth. And sometimes in the question, if you know the difference of two energy level, then your time to solve the question will decrease. So do remember these value. For example, if I want to find the energy difference between the first and the fourth orbit, right? So it comes out to be how much? It will be 12.75. Now, if I take the difference of the first two energy level, it comes out to be 10.2. So these values you can remember for hydrogen basically, right? Z will be 1. So then these are the values. Okay, right. Now let us see some of the illustrations or some of the previous year's questions based on the concept that we have studied in Bohr's postulates. The ratio for the speed of electron in the third orbit of helium positive to the speed of the electron in the third orbit of hydrogen atom will be. Okay, so what we have given, speed of electron in the third orbit of helium. So first of all, let us see the proportionality. So Vn is directly proportional to Z by N. And for helium positive, Z is equals to 2 and the orbit N is equals to 3. And for for hydrogen, Z is equals to 1 and N is equals to 3 in this case, not third orbit of the hydrogen. Okay, so we can say V1 by V2 will be equals to 2 by 3 divided by 1 by 3. So this comes out to be 2, and so the ratio will be 2 raised to 1, right? Option D. Now let us see one more question. So in Bohr's atomic model, the electron is assumed to revolve in a circular orbit of radius 0.5 angstrom. If the speed of the electron is 2.2 into 10 raised per, it is 10, right? 10 raised per 6 meters per second, then the current associated with the electron will be, right? So we know that the current is charge times the frequency, and frequency can be written as uh, reciprocal of the time period, and time period is nothing but 2 pi r and distance upon speed, right? So we can say the current will be directly proportional to Vn upon Rn, and Vn is directly proportional to Z by N, and Rn is directly proportional to N square by Z. So this will be Z square upon N cube, right? Directly proportional to Z square upon N cube. So we have given in Bohr's model, the electron is assumed to be revolved in a circular orbit of radius 0.5 angstrom. If the speed of the electron is 2.2 into 10 per 6, then the current associated. So we have to find the current. So speed is given and we need to find the current. Okay. All right. So we can directly use this relation, right? So radius is given to us, speed is given to us. Let us put the values. So E upon 2 pi, Vn is given as 2.2 into 10 raised per 6, and Rn is given as 0.5 angstrom. And we have to find the answer in milliampere. Okay, right. So can you see there is a 2.2? So we can write pi as 22 by 7. So let us again calculate this. So 1.6 into 10 raised to power minus 19 times 2.2 into 10 raised to power 6. And this will be 44 by 7 times 0.5. So this will be 0.1. So this will be 2. And we get 0.8 here. And this decimal will get cancelled out. So we have, so I will be 8, 7. So we have 8 and 7, right? 8, 7 is a 56 into 10 raised to power minus 20 plus 6 by 5. So this will be 11.2 into 10 raised to power minus 14, right? Let me check once more. So there is minus 19 is also there. Minus 19 minus 20 and then plus 6, right? E VM. Yeah, so it is in angstrom, right? So it is 10 raised per minus 10 is also there. So 10 raised per minus 10. So this will become plus 10 here, right? So will 1.2 into 10 raised per minus 4. So this will be 112 in okay sir, okay, right, 112 into 10 raised power minus 5, so which can be written as 112 into 10 raised power minus 2 times 10 raised power minus 3 amperes. So it is 112 into 10 raised power minus 2 times milliampere. So 112 should be the answer, right? So now let us see the fourth problem type, which based on the transition of the electron, and before that we'll understand some of the concepts. So what is excitation? So let us see. So we have given two energy levels. Let us say this is N1 and this is N2, and the electron is present in the lower energy level. Now, if we say give this atom energy in the form of photons. Now we have a photon which is having energy which is equals to the difference in these two energy level. So electron will gain that energy and it will move to the higher energy level. Now the energy of this photon will be E2 minus E1, and E2 will be minus 13.6 if it is hydrogen, right? If I consider hydrogen atom, 13.6 minus 13.6, 1 upon 2 square, and this will be minus 13.6, 1 upon 1 square. So this will become 13.6, 1 minus 1 by 4. So like this, we can find the excitation energy. Now what is ionization energy? Now suppose the electron is present in the nth orbit. Now we want to remove this electron from the atom. So the minimum energy required to remove this electron from the atom is known as the ionization energy. Now let us say this is the limiting orbit, which means n tends to infinity. Now if we supply energy in the form of photon, then the energy required will be 13.6 by n square in electron volt. Right? So this is the ionization energy for an electron which is present in the nth orbit. So do remember this. Now let us see the illustrations based on the same concept. So it came in 2021. Imagine that the electron in a hydrogen atom is replaced by a muon. The mass of the muon particle is 207 times that of the electron. So mass of muon is 207 times mass of electron, and its charge of muon is same as E minus E, and the ionization potential of this hydrogen atom will be, okay, right? So if we look at the kinetic energy, right, it is given as half m v n square. So the energy on, if you look at the mechanical energy, it will be directly proportional to the mass, right? So mechanical energy is directly proportional to the mass. So we can say the ionization potential that we have seen, say E is the ionization potential, which was 13.6 upon n square. Now this 13.6 will change, because in this 13.6 we have used mass of the electron. Now we have to use mass of the muon, and mass of the muon is 207 times the mass of the electron. So the ionization energy will be 13.6 into 10 raised to power, sorry, not 10, 207 times of 13.6 by n square. It should be like this. So if the electron is present or the muon is present in the ground state, the n will be 1. So we can say the ionization energy will be 13.6 into 207 electron volt. Now if I multiply 207 with 13.6, it will be close to option 2, right? Because other options are quite small. So option 2 is the right answer. I hope this concept is clear to you. Okay, right. An atom absorbs a photon of wavelength 500 nanometer and emits another photon of wavelength 600 nanometer. So electron is absorbing 500 nanometer and emits a photon of 600 nanometer. The net energy absorbed by the atom in this process is n times 10 raised to power minus 4 electron volt. The value of n is, okay, so assume the atom to be stationary during the absorption and the emission. We have to take the h value as 6.6 into 10 raised to minus 34, and speed of light as 3 into 10 raised to power 8. Okay. Now let us calculate the energy of the photon. So here we have to use this formula. Hc by lambda is the energy of photon. So this formula we're going to use. So energy of the photon which is being absorbed, and let me call it as EA. So it will be 6.6 into 10 raised power minus 34. C is 3 into 10 raised power 8 divided by wavelength 500 into 10 raised power minus 9. So this will be 19.8 upon 5 into 10 raised power minus 34 plus 8 plus 7. So this is the energy of the absorbed photon. So I can further simplify this. So this will be 3.96 into 10 raised to power, this will be minus 26 plus 7 minus 19. Now it is in joules. So if I want to convert this into electron volt, I have to divide by the charge of the electron. So this will become 3.96 into 10 raised to power minus 19 upon 1.6 into 10 raised to power minus 19. So if you simplify this, so 3.96 divided by 1.6, so it comes out to be 2.475. 2.475 electron volt. Now let us calculate the energy of the released photon or emitted photon. So 6.6 into 10 raised to power minus 34, or you can say, since energy is inversely proportional to the lambda, so energy of the emitted photon divided by energy of absorbed will be lambda of the absorbed divided by lambda of the emitted. So energy of emitted will be lambda A, lambda of absorbed is 500 nanometer divided by 600 nanometer multiplied with 2.475 electron volt. Okay, so if we simplify this, so we have 5 divided by 6 times 2.475, so it comes out to 2.0625. 2.0625. Now let us take the difference of these two. So 2.475 minus 2.0625, right? So this comes out to be 2.475, so 0.4125. So which is nothing but 4125 into 10 raised to power minus 4 electron volts. So the answer of this question, so the n value will be 4125, right? Now let us see another illustration. So light of energy 12.75 electron volt is incident on a hydrogen atom in its ground state, and the atom absorbs the radiation and reaches to one of its excited state. The angular momentum of the atom in the excited state is x upon pi times 10 raised to power minus 17 electron volt second. The value of x, h value is given in electron volt second, and c value is also given. Okay, right. So the electron is in a lower energy state, and we have given some energy in the form of photon, and the energy of the photon is 12.75 electron volt, and by gaining this energy, the electron move to a excited state from the ground state. So this is n equals to 1, and let us say this is n equals to n, right? Okay, right. So 12.75, this number sounds familiar, right? So let us see. It is the difference in these two energy level, right? 1 and 4. So we can say n is nothing but 4, because 13.6 minus 8.85 is nothing but 12.75 electron volt. So we know the electron will jump to the third excited state, or you can say the energy level will be 4. The angular momentum of the atom in the excited state is, so we know that angular momentum is given as nh upon 2 pi. So for fourth level, it will be 4h upon 2 pi. So this will be 2 times h upon pi, and h can be written as 4.14 into 10 raised to power minus 15 electron volt second divided by pi, and this will be 8.28 into 10 raised to power minus 15, which can upon pi, and this can be written as 828 into 10 raised to power minus 17 electron volt second divided by pi. So if we compare our result with this, we can see the x value is nothing but 828. So 828 is the answer, right? Now let us see the another concept. So what is de-excitation and the hydrogen spectrum? So de-excitation is when the electron jumps from a higher energy level to a lower energy level. So when electron jumps, then the photon is being released, and this photon will be having energy which is difference of these two energy levels. So E H minus E low, right? Right. So the spectral series, you must have studied this in chemistry. So let us quickly go through this. So when electron jumps to the ground state from the excited state, we can say we have a Lyman series. Say for example 2 to 1, from 3 to 1, 4 to 1, like this. Similarly, if the electron jumps from the first excited state or n equals to 2, then we have Balmer series. And when it jumps from to the second excited state, which is n equals to 3, then we have Paschen. And then if the electron jumps from n for n equals to 4, then we have bracket series. And when it is jumping from an excited state to n equals to 5, we have Fund series. Now let us see how we can calculate the wavelength of different lines in these series. Now the first line corresponds to, we will call it the first line of the series. And the last line is known as the limiting line. So let us see. For Lyman, 1 by lambda is equals to R times 1 minus 1 by n square, where n is greater than 1. N can be 2, 3, 4. So if n is 2, we will get the first line. If n is infinite, we will get the last line, which is the limiting line. And there is one more formula you can remember. If I substitute R is the Rydberg's constant, which is 10 raised to power 7 meter inverse. So if I simplify this, I will get 912 angstrom divided by 1 minus 1 by n square. So you can remember this formula if you want to have an approximation, right? You can use this to have some approximated value of the wavelength. Similarly, in case of Balmer, 1 by lambda will be R times 1 by 2 square minus 1 by n square, and n will be greater than 2. And in Paschen, 1 by lambda will be R times 1 by 3 square minus 1 by n square, where n is greater than 3. And in bracket, 1 by lambda is equals to R times 1 by 4 square minus 1 by n square, where n is greater than 4. And in Paschen, 1 by lambda is R times 1 by 5 square minus 1 by n square. So with these formulas, we can find different wavelengths. Okay, so now let us quickly see the question. And one more thing I forgot to mention. Smaller the energy difference, greater the wavelength, right? So the first line will be the longest and the limiting line will be the shortest. So for limiting, gives us shortest wavelength, and first line gives us the longest wavelength. So do remember this. Now let us see the questions. In a hydrogen spectrum, lambda be the wavelength of the first transition line of the Lyman. So Lyman, right? So, and do remember one more thing, Lyman lies in the ultraviolet region, and Balmer lies in the visible. Lyman, Balmer, Paschen, bracket, Fund, right? So this lies in ultraviolet, Balmer lies in visible, and these three lies in infrared. Do remember this. So in a hydrogen spectrum, lambda be the wavelength of the first transition line of Lyman. So electron is coming from 2 to 1, first line of Lyman. So I can say 1 by lambda is equal to R times 1 minus 1 by 2 square. The wavelength difference will be A lambda between the wavelength of the third transition line of Paschen. Okay, so in Paschen, this is Paschen, right? So in Paschen, we have 1 by lambda is equals to R 1 by 3 square minus, this is the third transition, right? So third will be 4, 5, 6 square, right? and uh, and second transition in Balmer. So in Balmer we have 1 by lambda r 1 by 2 square minus 1 by 4 square, right? Now let us say this is lambda 2, this is lambda 3, and this one is lambda 1. Or okay, let us keep it as lambda only, right? And we have given that the wavelength difference will be a lambda, right? So first let us calculate these values. So we have 1 by 9 minus 1 by 36. So this will be 3, sorry, this will be 4, 3 by 36 times r, or we can say r by 12. And this will be r times 1 by 4 minus 1 by 16. So this will be 3r by 16. Now the difference of lambda 2 and lambda 3 is a lambda. So lambda 2 is 12 by r, or I can say it is 36 by 3r, and lambda 3 is 16 by 3r. Now the difference of these two is a lambda. So a lambda is lambda 2 minus lambda 3, which will be 36 minus 16 upon 3r. So this comes out to be 20 upon 3r, a lambda. And what is lambda? So lambda will be 4 upon 3r, right? So let us substitute the value. So a is equals to 4 upon 3r is equals to 20 upon 3r. So this 3r will get eliminated and we will get a as 5. So 5 is the answer. Now let us see the next question. The recoil speed of the hydrogen atom after it emits a photon in going from n equals to 5 state to n equals to 1. Now let us see. So electron is coming down from n equals to 5 to n equals to 1. Okay, so now let us find the energy difference. So it will be 13.6, 1 minus 1 upon 25, right? So this will be 13.6 times 24 upon 25 electron volt. Now that is the energy, right? So we have an atom, and this atom releases a photon, and this photon is having an energy E. Now what would happen? So if I apply momentum conservation for this system, now if I consider this as my system, so this is photon and this is atom. Now the atom will go in the left direction if the photon is going in the right directions to conserve the momentum. So we are assuming that the atom was at rest initially. So we can say momentum, the magnitude of momentum of atom is same as the magnitude of momentum of photon. And you know that for photon, momentum is given by E by C. And the momentum of a particle will be, so for atom it will be mass of the atom times the velocity of the atom. So this will be E by C. And if we substitute the value, we need to find the recoil speed of the hydrogen atom. So in hydrogen atom, the mass of the hydrogen atom will be nearly 1.67 into 10 raised to power minus 27, which is nothing but the mass of the proton. So V is equals to 13.6 into 24 upon 25. This is in electron volt. Multiply this with 1.6 into 10 raised to power minus 19. Now divide this by 3 into 10 raised to power 8 and divide this by the mass of the atom, which is 1.67 into 10 raised to power minus 27. Now when we simplify this and calculate this, we will get 4.17 meters per second. So option 1 is the right answer. Now let us see one more concept. Suppose the electron is present in nth orbit, right? And let us say this is the ground state, n equals to 1. So we need to find how many possible different types of photons can be emitted when the electron de-excite from this excited state. So how many different spectral lines can be produced? So you should remember, for example, let me give you the illustration. Let us say the electron is in the 4th level. So this is second, this is third. So if electron is in the 4th level, then the electron can directly go to the 1st level. or the electron can go to the second or to the third. Suppose if the electron is in the third level, it can directly go to the first level or it can go to the second level. So if the electron is in the second level, it can go to, it has only one transition, that will be to the ground state. So how many lines are there? So it will be 3 plus 2 plus 1, so that will be 6. So you should remember, if the electron is in nth state, how many possible photons can be generated, different energy photons can be generated? It will be n into n minus 1 by 2, right? So number of spectral lines. So do remember this formula. So if electron is in the fifth level, so it will be 5 into 4 by 2, so it will be 10, right? Okay, now let us see the fifth type of problem, which is based on a hypothetical Bohr model. So now let us understand what is a hypothetical atom. So in a hypothetical atom, usually we have given the force with which the electron is revolving around the nucleus is not inversely proportional to r square. So that is not there in a hypothetical atom. So some other force will be given. For example, F can be given as K upon R, or some other relation, or it will be F will be K upon, say, R raised to power 3 by 2. So different combination can be given to you. Or sometimes the potential energy is given to us. So you will be given to you as, say, K by R raised to power 4. And then from U we can find the attraction force or the conservative force. It will be minus du by dr. So from here we can find it as K, and this will be minus 4 plus 4K by R raised to power 5. So like this we can find the force. Then we equate this force to the centripetal force, right? So 4K by R raised to power 5 will equate this to mv square by R, and then we'll again do the same derivation that we have done in the previous part of the video, and we can again form the relation. So here in case of hypothetical atom, our relation whatever we have derived are not valid. So this we can apply. So like this we can apply the first law, or the first postulates, and for the second postulate is applicable. So mvn rn is equals to nh upon 2 pi. So this postulate will be applicable. That modification we have to do. Now let us see the illustration which will give you the idea how to apply this concept. A particle of mass m moves in a circular orbit in a centripetal central potential field, which is u, which is u naught r raised to power 4. If the Bohr's quantization conditions are applied, radii of the possible orbit Rn varies with n raised to power 1 by alpha, where alpha is. So we have to find the value of alpha. So u is given as u naught r raised to power 4. So we can find the force, that will be minus du by dr. So it will be minus 4 u naught r raised to power 3. Now this force is responsible for providing. So this force is responsible to provide centripetal force. So we can say Fc will be equal to 4 u naught r cube, or we can say Rn cube, and this will be mvn square by Rn, right? So now we have a relation between the speed and the orbital radius. And we have to find the relation of R and the n. Okay, so we can say R n raised to power 4 is directly proportional to Vn square, and we know that mvn Rn is equals to nh upon 2 pi. So we can say Vn Rn is directly proportional to n. Okay, so we can say Vn is directly proportional to Rn raised to power 2, right? So let us substitute this in this proportionality. So it will be Rn raised to power 3 is directly proportional to n. So Rn will be directly proportional to n raised to power 1 by 3. So if we compare, 1 by alpha is 1 by 3, so alpha will be 3. So 3 is the answer. Now let us see one more case. Suppose an electron is attracted towards the origin by the force. So we have given force as K by R, and where K is the constant, R is the distance of the electron from the origin. By applying Bohr's model to this system, the radius of the nth orbit of the electron is found to be Rn, and the kinetic energy of the electron to be Tn. Then which of the following is true? Okay, so we know that this force is nothing but the centripetal force. So K by Rn is equals to mVn square by Rn. So this R will get cancelled out. So we can say Vn is nothing but constant. If Vn is constant, we can say kinetic energy, or here it is given as Tn, is constant. If kinetic energy is constant, Vn is constant, and we know that mVn Rn is nh upon 2 pi. So Vn is constant, so we can say Rn will be directly proportional to n. So option B is the right answer. Now let us see one more illustration. In the Bohr's model of hydrogen-like atom, the force between the nucleus and the electron is modified as this. So we have given F as E square upon 4 pi epsilon naught, 1 by Rn square plus beta by Rn cube. So I'm writing this force for the nth orbit. Now this will be equals to centripetal force, mvn square by Rn. Okay, so now what we can do, let us multiply left hand side and right hand side with Rn cube, right? So it will be E square upon 4 pi epsilon naught, and this will be Rn plus beta equals to mvn square Rn square. Now if I multiply with m and divide by n, I will get this, right? And mvn Rn is nothing but the angular momentum. So it will be nh upon 2 pi. Okay. So we have to find the radius of nth orbit. So we have to find this Rn. So we can say Rn plus beta will be n square h square upon 4 pi square m 4 pi epsilon naught upon e square. So this 4 pi will get cancelled out. So we have epsilon naught h square upon pi m e square times n square. Now this pi epsilon naught h square upon pi m e square is nothing but the Bohr's radius. Bohr radius is the radius of the first orbit, which is 0.5529 angstrom. So this is given as a naught in the question. So we can say Rn will be a naught n square minus beta. So option C is the right answer. Right? So I hope whatever concept that we have discussed in this video are clear to you. So if you like this video, I'm pretty sure you'll also like Prague-based unique approach to guide student for their last mile journey. So if you are a student who has been preparing for JEE or NEET and you are going to write your exam in 2024, then Prague is the best platform to further refine your preparation. Other crash courses which cover 100% of the syllabus in less than 2 to 3 months, and that syllabus you took around 2 years to prepare, or more than 2 years. So it is very difficult for students to absorb 100% of the syllabus in that short amount of time. So at Prague we follow a unique approach to cater this problem. So at Prague we have a 3-step process. In step 1, a senior faculty will sit with you. He will assess your weak areas and he will guide you what are different consistent topics that you have to prepare to ace in your exam. And he will prepare a concrete plan and he will allocate the number of classes required for that. So once that plan is prepared, now we'll move to the second process, and that will be one-on-one online classes. So in one-on-one online classes, the faculty will be aligned with you, and that faculty will guide you how to apply those concepts in which you are not good at and how to solve a problem effectively. So then we move to the third process or third step. In this step, we'll align you in a test series. So where you can see where you are currently standing and how these classes are helping you out. So you can have a full syllabus test, or you can also give part test for a chapter test. So by using this approach, Ashish Mishra was able to maximize his score in JEE Mains and JEE Advanced. And at present, he is studying mechanical engineering from IIT Madras. So if you want to maximize your score in this last mile journey, so I have given a link in the description box. So you can click on that link and book a session with us. So one of my teammates will get in touch with you and he will guide you.